I'm Jobst Heitzig.
And I'm Jonathan Donges, and we represent the copan collaboration.
We'll be talking about Earth system modeling with complex dynamic human societies, the Copan Core World Earth Modeling Framework.
We now live in the Anthropocene, a new geological age where social dynamics has become a dominant process in the Earth system, a lot of it even larger than natural processes that have been going on for the past millions of years. Now, this Anthropocene has come along with dramatic changes such as anthropogenic climate change, global warming, and biodiversity loss, for example, and has created huge challenges for human societies. Addressing these challenges requires modeling, computer modeling, and there is already a lot of modeling of the climate system, of ecosystems, but an integrated modeling of social ecological interactions and dynamics on the planetary scale is so far largely missing. So we think that novel so-called world Earth models are needed for modeling this Earth system dynamics in the Anthropocene, because current models of global change do not account for socio-cultural processes that are decisive in the Anthropocene. There are social network dynamics, opinion formation, policy processes, for example, social tipping points that may lead to solving the climate crisis, for example, but also might be actually undesirable, like a collapse of societies, as arguably has been experienced in the past in many societies. And also the interactions between tipping points, for example, like the ones that we show in this figure here to the right, where we are interested in the Dominoes project, currently researching how the tipping elements in the climate system, such as the Greenland ice sheet, for example, could lead via actual climate impacts, but also anticipated future impacts to changes and potentially also social tipping in attitudes, policy and behavior, and then how this feeds back potentially to the Earth system via greenhouse gas emissions, land use change, and other impacts, for example. Now, really, in understanding this Earth system dynamics in the Anthropocene requires closing the loop in Earth system science, in Earth system analysis. It is not enough to just connect, let's say, models of social dynamics in a linear way to an existing Earth system model. It is important to look at the feedback interactions into the complex co-evolutionary dynamics. It is important to look at human agency more explicitly, diversity and inequalities in, for example, socio-metabolic classes, other types of resource consumption or attitudes, social norms, cultures, and also to emphasize the networked aspect of human societies in the Anthropocene. Bringing this all together could enable modeling and analyses that can actually study the state space of nature and societies as it is depicted here, to find out what are desirable pathways that lead towards something like a safe and just operating space for humanity that has been argued to be delineated by planetary boundaries on the environmental side and social foundations on the social side, as they are encoded in the Sustainable Development Goals. But also such an analysis could find out where critical dangerous domains are that have to be avoided, where tipping points are, where critical path bifurcations are. And we have hosted a Loops workshop series on these topics during the past years, where a lot of this information has been gathered. And towards actually building such models, it is important to get an idea, to get an overview about what are actually the relevant processes of Earth system dynamics in the Anthropocene. Our taxonomy paper that is currently under discussion in Earth system dynamics discussions is that to propose 3 different process taxa that we call the biophysical taxon, the socio-metabolic taxon, and the socio-cultural taxon. And the biophysical taxon contains models of natural Earth system processes such as atmosphere and ocean dynamics, biogeochemistry, for example, and ecology. Socio-metabolic taxon includes models and modeled processes of human environment interactions, for example, for social reproduction, maintenance, and growth, such as infrastructures, demographics, agriculture, trade. And finally, the socio-cultural taxon contains modeled processes of behavior, of interactions between human minds and their immaterial legacies, such as behavioral change, for example, decision-making, opinion formation, social network dynamics, the dynamics of policies, governance, and even values. In this more conceptual perspective here, let us look at how these World Earth models that we propose fit into the landscape of models that are currently used for Earth system analysis. Classical Earth system models are process detailed in the biophysical process taxon, in our terminology, and they are forced by emission and land use scenarios, by externally forced pathways that come from economic models. And this forcing is playing out in the socio-metabolic domain. There's no dynamics in the socio-cultural domain in these models. The macroeconomic integrated assessment models that are used for evaluating the costs of climate mitigation, for example, they are process detailed in the socio-metabolic and economic domain and contain more stylized dynamics in the biophysical one, while the socio-cultural dynamics is mainly captured by prescribed narratives, like the shared socio-economic pathways, SSPs, that are used by the IPCC. And now the idea is that the World Earth modeling that we propose and that our Copan core framework can implement, that they complement these existing models by allowing for representing the three different taxa in a balanced, in a compatible way. And we propose that probably a first good step would be to focus on models that are process detailed in the socio-cultural domain, because this domain is actually what has been missing so far in the Earth system modeling landscape.
To model this type of models that are needed, we developed a modeling framework at PIC, which is called the Copan core framework, and it is based on this conceptualization of process taxa that we speak about already, and corresponding entity types, which are in loose one-to-one correspondence to these taxa. We support individuals, like households or firms, social systems representing countries or cities, and cells, which represent spots on the Earth's surface and are typically used in Earth system models. The framework also supports all kinds of different modeling approaches, such as agent-based modeling or algebraic equations, differential equations, and so on. The design is basically object-oriented, as is suggested by the entity types, and it's also very modular, and we realize this modularization by multiple inheritance. Currently there's a Python reference implementation, but we aim at implementing it in C++ for performance reasons. There's an extensive documentation available on GitHub, and it also supports parallel simulations on high-performance clusters to perform Monte Carlo simulations, for example. We aim at a strong community integration because we're a small team. We have a lot of partners here shown on the right, and therefore we also have spent some effort into devising a role model where different user types can interact with the software framework in different ways, like, for example, model end users using scripts to import existing models and run simulations, and on the other hand, framework developers who really advance the framework itself. In between, there are component developers or model developers who develop the actual model logic. We host the whole thing on GitHub, and we try to be very interoperable with other existing models, such as climate models and land system models and so on. It's all open source, of course, as is the current standard. Just to illustrate what the framework can do, let's look at very briefly a small toy model which contains all kinds of different processes from the different taxa and also different modeling approaches. Here you see, for example, economic components, a global carbon cycle, natural component, but also social processes like voting and so on. Just as a teaser, here's some exemplary results which show that, in particular, including social-cultural processes makes a big difference in this model, at least. On the left column, you see model runs which do not have social processes such as voting and environmental awareness formation. And in the bottom row, you see certain developments in, for example, the global carbon stocks, leading to a lot of climate change here in this run. On the right column you see if we switch on the voting and the awareness formation and also the social learning processes, then you see in the upper row that a lot of things happen in that taxon. People become more environmentally friendly, vote for all kinds of climate policies, and as a consequence in the bottom row you see that the climate change is much smaller.
In summary, I think we have argued that computer simulation models and big social ecological data are both essential tools for understanding future trajectories of the Earth system in the Anthropocene, and the new class of World Earth models that we advocate for is needed to capture aspects of socio-cultural macrodynamics as well as their co-evolution with the biophysical Earth system, both using a complex systems approach. And key research topics for this World Earth modeling include, for example, the analysis of Earth system stability and resilience on different levels, social ecological tipping points, potential cascading dynamics, particularly also really a focus on social tipping points that could bring about societal change in the face of ecological crisis, and the topic of safe and just operating space. Does it exist? What are the stability and resilience properties of it? How is it interacting? How is it constrained by planetary boundaries and the SDGs? And finally, we would really like to thank you for your attention, point you to all these websites and the Copan core framework on GitHub, the papers leading to it, and finally a special issue in the journal Earth System Dynamics that we have co-edited together with others that is about really the topic of social dynamics in Earth system modeling. Thank you again.